universe is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light.
Well, here we are again. And hey, hi, Tara. How are you? Uh-oh, can't hear you. You're muted.
I'm muted.
There
I'm
you go.
unmuted now. Sorry. Hey, how's it going?
Good. How are you?
Good.
It's nice to see you. Daryl's taking a night off, so it's
That's what I
just you and
heard.
me, kid.
Okay, all right. That's
How about that?
awesome. Me and everybody in chat and then out there in the universe. So
That's
awesome.
exactly right.
We're still in good company. So
We are,
that's
you
great.
know, and I hope you have some good questions tonight too,
Oh,
because
I hope so too. Yeah.
we got an awful lot of really cool stuff going on tonight. And do you guys,
Cool.
I thought tonight we're calling it Astronomical Potpourri, but you know what? We may deviate from the main topic a little bit. But the truth is, the James Webb Space Telescope, okay, has made some astonishing finds, and we're going to talk about them and show them to you. I think it's just amazing what it's done, you know.
Can't wait.
Yeah. But first, I just want to let you guys know, we and Tara's involved in this along with Marianne, who is with the iDetective show. Marianne and Tara have joined forces with me, and we have SkyTour live stream 501c3. We have our own not-for-profit company, and we're using it to actually get the astronomical outreach message out to everybody under the sun. Anyone that'll listen and anyone that loves astronomy is free to join us. And when I say free, it is free. We do have a Patreon, so people can subscribe if they want, and they get these beautiful high-resolution pictures that are the size of their freaking 2 or 3 computer screens if they want them. Yeah, right. I know.
Yeah, okay.
But we also have a lot of swag and stuff like that people can get as well. And we did that because it's costing us to bring this to you. We have to pay for the internet each month. It's $110 a month, and we have 2 sites now. One here in the East, which we've always had, and the Arizona site, but we have another site we're looking at. So we're looking at 3 total sites, not to mention the 4th one that we want to open in the Southern Hemisphere. Shh. Don't tell anybody. Guess I already did, huh? But we don't have a specific site picked out yet, but I want to have it down in Oz somewhere in Australia.
Well, I volunteer to go scouting for you if you like. So.
I bet you would. You know,
why not?
And we might be sitting right next to each other on the same plane, okay? Because I'm gonna scout too. There's a few sites down there actually that I've been looking at, and again, that's long term, but it's really to cover cool. the entire planet, right, Tara? I mean, we want to cover the whole planet with what we do.
Why not?
You know, and I have to give you kudos too, and Marianne, because Marianne's entertaining some friends tonight, so I asked her if she could come on briefly, but she can't. Okay.
Darn it.
Yeah, that's okay.
She's always busy, though.
Yeah, she is. You know, she's supposedly supposed to be a retired police officer. I haven't seen it. Have you?
Well, anybody who's retired knows you get a lot busier once you retire. So
that's very true. That's very, very true. Mm-hmm. But I was going to ask her to talk a little bit about the whole process of making us from a YouTube channel into a real organization. And it's you, me, and Marianne right now, and maybe we'll add more people in the future. Who knows? Yeah. But I do know that what we've got going for us is excellent equipment, excellent sites, and hopefully excellent knowledge.
Well, it's a process, and
it is.
We've got all the time in the universe.
Yeah, that's true. That's true. And you know what? I think people probably want to know, what the heck is that orange thing behind your head? I'm going to guess it's one of your neon things, right?
Yes, I just picked this up last week, and it was in a exhibit.
Well, make sure people understand you made it.
I did make that. Yes,
yeah, that's right.
Yes. I
That's
am a
really cool.
neon artist, and so it was really fun. I got to put my work in the show with another lighthouse exhibit, so it was
That
really
is
cool.
so cool.
Yeah,
And well, I
very
always knew you were
fortunate.
I know always knew you were very bright.
Uh, well, neon, it's
Really.
funny how I'm so attracted to it, it's part of the universe, and
Yeah,
it's just
that's right.
yeah. Hey, look who's here.
Hey, look at who's here. It's Amanda. Hey,
Yay.
how are you down there?
You creative people looking
Aw.
for help. I decided to pop in and
Awesome.
show my support. Sorry, I'm running late. The code wasn't working to get in. I slept in. I overslept. I'm sorry, but I'm here.
I'm glad you're
here to
here.
learn.
I'm glad you're here.
Her cat ate her code.
Oh,
Yeah. My cat
Yeah,
ate
that-
my homework, so if I don't
Yes.
know what's going on in the universe today, blame
I've
Smoo.
never heard a cat eating homework. It's always a dog. Okay, so don't start playing games like your cat can equal a dog in terms of eating homework.
Cats can
Oh,
do other
cats are
destructive
so
things on
superior.
homework. Yes.
Oh man,
My cat wrote my homework for me. He's much smarter.
Okay, well, that's a very good answer to that.
Well, maybe cats can see colors we can't, and they can
Mhm.
see
Infrared, like the James
Yes.
Webb scope,
Yeah.
maybe they can.
That's right. So,
I'm gonna name my next cat James Webb.
oh, that would
Oh,
be the
cool.
coolest thing if you actually name him
Mhm.
Webb.
Oh, what?
No.
Maybe
Webb.
I could buy a
Webb.
tarantula.
Webb.
Name him James.
Oh, that's a pretty good idea.
Ah, God, you guys are
Speaking
clever.
James, the web
Speaking of
creator.
tarantulas, speaking of
God.
tarantulas, right? I mean, you know the
Uh-huh.
story, Amanda. I think that Tara and Marianne and Dale were out in the building doing some service on the telescope out there, and underneath the computer mount, where the computer was, there was this gigantic palm-sized tarantula just sitting there. And I was on the
bothering anybody. Yeah.
no. They're actually very docile creatures, and they don't bite unless really provoked. So, but I'm on the phone with Marianne because she's trying to help me figure out and show me what's going on so that they can take the scope, mount it back on the mount and everything because we had to have it serviced. But Marianne gets all in a panic. She starts screaming, and I thought she fell down. I thought the scope fell on her. I thought she was about to die. I had no idea. She's running, and all I see is I just see this. I see this. Whoa! Okay, the screen going absolutely wild. I'm going, Marianne, what's wrong? What's going on? And she's going, I can't believe it. That thing. What thing? What are you talking about?
She was going,
She couldn't say the word tarantula. She was so nervous and scared. And they went back in, and I saw, it's like, oh, how cute that thing is. It just wants to eat food. It's not interested in humans. So Dale took the tarantula and let it crawl up his arm.
He did.
And he took it outside and set it down on the outside.
Brave man.
The one thing that threw me is that palm size. That's not really an accurate measurement, unit of measurement. And of all the things, like I get an arm's length or a finger's length or something like that. But who's ever going to put a tarantula in their hand, in their palm to know, oh, that fits?
Okay.
Is that your spider measuring ruler?
This is a ruler, okay. And this tarantula was about 5 inches long, right there.
So is that an arm's length, like when you're measuring things in the atmosphere too? I mean,
No.
a hand length or
arm's length with a fist. Okay, when you do this with a fist, okay,
right?
That fist represents 10 degrees at arm's length. You do this, if you open your fingers, okay, that represents 20 degrees. Okay, so you actually can use your hands as a very rudimentary measuring yardstick when you're trying to measure stuff in the sky. But
not tarantulas.
No, for tarantulas, most people measure them with a stick, but they're chasing them with it usually, and it's not fair because these guys are just so cute. I did want one at one point. I wanted to get a tarantula, but my
friend had a tarantula named him Boris. For any Who fans out there, Boris the Spider. Great little song.
Great little song. Great little.
Well, that's
spider.
how I feel. You're just like, no, where's he gone now? I can't see. Yeah, that's
Boris the Spider.
That's a great. I would suggest anyone go check out that song, Boris the Spider by the Who.
Yeah.
It's funny, it's cute, but the imagery might provoke nightmares, so I'm not to be responsible for that.
Actually, with our producer Bill, he would probably have problems with it. He's probably nodding right now like this because he says, "No, I'm not going to touch those spiders." But he doesn't know. But eventually, we're going to actually put a spider in his house and tell him there's a spider in his house. Maybe a tarantula.
Hopefully, it's a plastic one.
Maybe.
Get one of
Don't
those
tell
remote
me.
control ones that
Oh,
you can
God.
crawl
God.
around and
It comes
they stick to
upon
the
him.
They hop.
ceiling.
They hop.
Oh,
Oh
God.
gosh.
Oh, so
Mm-mm.
we're talking about tarantulas because we're talking about the observatory, and
Right.
that's where that was. And of course, the tarantula was removed very, very easily
Lovingly.
and lovingly. And the thing, again, they don't mind people. They just,
That's cool.
they have to be really, really, really irritated to bite someone. And when they bite, it's a sting and it doesn't kill you. The tarantulas in the Southwest won't kill you.
It just gives you the willies.
It gives people the willies, thinking of these big long fangs just digging into them and right in their eye. Oh yeah, it's just like nightmares.
Yeah.
So that was for Bill.
Okay.
He's probably listening and he heard this. He's like, no, right? I know, Bill, you are. I know you are. I know he's over there. He's always listening. So let me get into the topic of tonight because I think we better, because Bill's probably sitting there shaking right now because he hates spiders. What we're talking about is, of course, we're talking about Sky Through Live Stream, which is our remote observatory. It's a remote system that I set up because I just didn't want to be in the cold anymore. And I just didn't want to be looking in light polluted skies anymore. Now, Amanda knows, because Amanda was like the first co-host we ever had on Sky Through Live Stream, I believe. And she was here with me when I was out in the front of my yard here, 80 feet or so from the house, and inside an actual dome that I had built in the front yard. I put a dome up and I had the telescope in there. And people say, well, just put a heater in there. And the answer is you can't put a heater because the air has to be the same temperature as the outside. The ambient inside has to match the ambient outside. Otherwise, when you open that slot for the telescope to look out, the hot air inside is going to go racing out that opening, and everything in all your images are going to be just doing this. See, all your images are going to be doing that. Okay.
And you're doing that too because it's freezing.
That's and I was definitely shaking and everything. But Amanda remembers those times when I was saying, and now we're going to look at the Orion Nebula, and it was like, ugh. It was literally 15 degrees, So
you're giving me all these flashes of like silly things I've been watching. I feel like, Chica, I was here first. I have seen everything.
You saw it all first. There's no doubt about it. Yeah, and
that's neat.
So I decided I'll keep the telescope out in the dome in the front yard here. We called it Sky Tour East, and I'm going to use Wi-Fi to connect to the building. So I used Wi-Fi from right where I'm sitting in my marvelous little bunker-y place. And
it's a ship.
It is. It's a ship. You haven't been here yet, but Amanda, were you here? Did you come here?
No, I didn't.
No, you didn't make it here from Pine.
No, that was a year before I went. When
Yeah.
everyone got little replicas of, it wasn't the ISS, the satellites, something.
It was the Google Earth satellite.
Yeah. It was a what satellite?
It was the Google Earth satellite. Yeah.
It was I knew it was a specific thing that people would recognize, not just a satellite. Yeah, but I couldn't remember. I never got one.
Well, if you were here, you would have.
Just want to throw that out.
I didn't get
Years
one either,
later,
just so you know.
Yeah. Okay. Yeah.
And you gave them all prints of craters of the moon, and I wanted
No.
What do you mean? No.
I didn't give everybody prints of the moon. I gave Keith Ickes from P&K Space Imaging. I gave him craters of the moon. I gave Bill one because Bill was allowing us to be in Pine Bush, but I didn't just give them away.
I thought everyone that visited you got one. Didn't like Heidi get one? I can't remember who all was there. I know Heidi was there because she just loved the property. I think she was like dancing in your field.
Maybe.
I thought a few people went, and who was Eric there, and was Jade there? I can't remember.
Yeah, you're right. I think you're right. Actually, I think you're right.
I know you gave Keith something that he had to take back in a big pickup truck.
Yeah.
What was that? That was something massive. I can't remember, a prop from a movie or something. Or
it was it was actually the second copy of the Jupiter 2 from the original Lost in Space TV series.
Very cool.
I had a guy, he drove up the driveway with it in the back of a tiny pickup truck, and it was barely strapped in. And he said, "Hey, here, you want this?" I go, "Oh, okay." And I rolled it into my backyard where it stayed for 10 years. I never did anything with it, so I gave it to Keith.
Wow.
I told him,
right place at the right time.
Yeah, I said, if you sell it, I'll 50%, man. That's all, But I gave it to him. So anyway, I might have done that. but the thing is, that has to do. It all had to do with the observatory, but going from the Wi-Fi out on the front yard to going fully remote. Now that was the next leap. So I took that leap by investing in some technology that literally cost me nothing. I learned how to write programs for these little microcontrollers called Arduinos. And I wrote an observatory control program using the Arduino Uno, which is a little tiny square circuit. Okay. And then I have a laser cutter here for my shop. So I laser cut this box to put it in and all that. It looked really cool. But it didn't work right the first couple times. So I had to work at it. And it took me a couple months to debug all the code. So I finally did that. And now I use that as the remote control program to connect to the building out in Arizona. And to connect to the building here, well, the building here is right now removed because we outgrew it. The dome became actually too cumbersome, and it didn't withstand the winter weather very well. So I sold it to somebody down in Long Island, New York, and he's very happy with his new dome.
Wonderful.
That he got from me. Yeah, I sold it for almost what I paid for it. It's actually quite rare, and he'll set it up, I guess. But I'm building a different building. And I've got to do the similar kind of thing as out in Arizona where the roof comes off. But out there, I can afford to have these posts where the roof rolls on to these, the second section of the roof. And it just like rolls out and lands hanging out over the desert a little bit. And it's on these posts, these big, giant 6x6 posts that the roof is resting on along these rails. But here, I didn't want those extra posts in the ground. Because out here, the ground is not as stable. And in the wintertime and in the summer, things swell, they freeze, and those posts will move. And if my yard and posts in the yard and under sheds are any indication, it would be good for about a year. And then I'd have to revamp the whole thing. So instead, I made it all self-contained. I made it so that the roof is going to be lifted off by these linear actuators that are all on the building itself. It's going to lift off the roof and pivot it down to the side. And pick it up and put it back on the building. And these linear actuators can each hold 600 pounds. So the roof is going to be maybe 150 pounds. But it's designed to be able to handle heavy snowpack if there was snow. Let's say there was 3 feet of snow on top.
There's 3 feet of snow on top.
She said it, and okay, now there is. Well, these things can. That's right. These things can push that roof off, even though there's 3 feet of snow. And of course, it'll serve to plow the roof because it falls to the side, snow falls off, roof goes back on. Okay, so that's the new one for here. I had to redesign the whole idea from Arizona because of the weather conditions. Arizona is actually remarkably stable in the desert. It's wet. Like today, it rained like the dickens.
It sure did.
At the site, as she would know, being in Arizona. Okay.
And
they're happy about the rain. Me, as an astronomer, we hate the rain. We also hate drought because we know what it means to everybody else. So, we'll have some clear skies coming up. And what do you see when you come to SkyTour? SkyTour Livestream is a channel on YouTube, by the way, and we actually have a wonderful portal site, which you see right there down the bottom now. It's skytourlive.com. And skytourlive.com or skytourlive.org will bring you to the same place. And skytourlive.com is the place where you go if you want to go to our Patreon and subscribe, where you want to go to get to our channel, where you want to see some cool pictures, where you want to go check out the database that we make available to you for free with every observation over the last year and a half. Okay. It's just that the Patreon subscribers get more. They get the finished, highly processed images. But it's to the layperson looking at the images on the screen that we provide at the conclusion of doing a single object. It looks quite good, and
it's amazing.
So, but we're providing them big, giant resolution and with color enhancements to more appropriately color the nebulae and galaxies, enhancing spiral arms and galaxies and stuff like that. And when I talk about, enhancing objects, I'll give you an example. Here is an object that we took. This is the Orion Nebula. Okay. You can't tell. I mean, the Orion Nebula, you're used to seeing that lower part being splayed out and you see a few things, but you're not used to seeing all that brown dust around it, and not used to seeing that other nebula up top. Now,
So is that the Running Man? Is that what that is? Look at him running through it. You can really see it.
Yeah.
From this perspective. Wow.
Yeah, that's the Running Man. Now, those white streaks you see on the left side, those are actually satellite trails. And we also get satellites coming through and anomalous things. So if you're interested in UFOs, you can come watch things travel through the field for almost every exposure. It's actually quite cool, But these nebulae, these dark nebulae like this, we call them, these dark brown areas, these areas, this is where it's at for me as an astronomer, because this is where we come from. Okay, these dark nebulae have all the fundamental materials and composition of materials that provides all of the raw materials that make stars, planets, entire systems, and us. So these dark clouds are things that we sometimes go to look for in the night sky. And at our site out in Arizona, that's so dark. Okay, this photo right here is actually a mosaic of 4 photos. Okay, and this no wait, I'm wrong. This is one photo. My mistake. This is one field view for our system. I apologize. And this one is this one here is a 40-second shot. So we opened the camera and talked for 35 seconds, and when 5 seconds more showed up, boom, we have this at us, looking at us. And then we took a bunch of those and we stacked them together. And by stacking them together, what that does for us is it allows us to remove the noise that you might see in the background of all the shots, So this is the Orion Nebula with the Running Man at the top there, and it's dust. Now we also look at galaxies. Here's one. This right here is called the Sculptor Galaxy, and it's got its spiral arms. You can see the dark clouds in there. Those dark little lines, those are dark nebulae, just like we see in our like this. When we look at the Orion Nebula, that those dark clouds there are reminiscent of the dark clouds here, just close up, looking at them zoomed in.
Right.
Okay. So this is the Sculptor Galaxy. This I just imaged, actually. This is recent. And then another one I imaged recently is this one.
Ooh.
Imagine this red. What is that red? People say, what's the
neon? Red? Is it neon?
It's yours, right? It's no, but if you look at the color of the nebula and the color of Terra's, stuff there in the background, see Terra's background.
Yeah,
stuff
there it is.
It's the same kind of color. But we do see glows of neon, and it does look that color in space, but usually associated with supernovae explosions. This right here, again, notice more dark clouds. Those dark clouds at the top, where that red stuff is actually hydrogen, and it's glowing because the hydrogen has been ionized by hot young stars in the area. And where we see the bluish kind of nebulae, they kind of look white in this image. Those are areas where there's more dust than there is hydrogen. And the dust is very, very good at scattering the blue light from stars. So we have what we call reflection nebulae, which are these blue ones, and then emission nebulae, which are the red areas, right? And then, of course, silhouetted against the red at the top, you see this dark black, again, fundamental composition of materials to make stars and planets, these dark nebulae. This is just astonishing. It's the most amazing sights.
I have some questions.
Sure.
Because, well, looking at this, if you didn't know anything, I would say this looks like a very violent picture. Like the red looks like explosions or new star creations or like the beginning. But because I've been saying, "Oh, be a fine guy, kiss me" for so long, I'm thinking would the blue areas of the sky not be the violent kind of explosions? Because the blue is bigger and hotter. So just looking based on color, I would think red is the violent explosion and blue is kind of like the cool down, things are starting to form, kind of relaxed phase. But if blue were bigger and hotter, then am I thinking of this backwards? Like, what would a stellar nursery be? Would that be either, or would that be just kind of white?
No, see, it's a different topic altogether, a different avenue of a similar science. When you have a hydrogen atom and you really pound it with heavy duty ultraviolet light that's really powerful, the electron around the proton, there's one electron in there, it zips
take this
around.
picture down
Yeah,
so I
I'm
can see
gonna
your hands. Yeah, okay, go.
the electron is going around the proton. Okay. And if you hit it with ultraviolet energy, it can bounce off the atom, leave the atom, because it gains so much energy. That leaves just the proton now. And the electron will eventually lose energy and come back down into the atom. As it bounces back down into the atom with every step, it's like you falling down the stairs. Let's hope it doesn't really happen. But if you fall down the stairs with
Knock on wood.
Yeah.
Not going to reenact that for a video. Sorry.
No, that's fine. But as you fall down the stairs, with every fall, it's hurting more and more and more, and you're getting more and more wiped out from the fall. So in the same way, the electron's doing the same thing, but instead of being hurt, it gives off a little light. Okay. So as an electron drops down into the hydrogen atom, it bounces down in, it's called a cascade. It cascades down. And most of the electrons in hydrogen, when they're treated like this, bounce to the same level. And that level is level 2. N equals 2. N is in November, equals 2. That's the second energy level in a hydrogen atom. And when you have an electron bounce to that level, it gives off a very characteristic color light, which is red. And that's why nebulae are generally red, because the predominant reaction, the predominant, what we call a recombinatory energy that's given out when an electron bounces back down into the atom is going to be this red color, because it's going to the same spot in the hydrogen atom. Pretty cool. Now, the blue, on the other hand, there's no processes like that going on. There's no ionization going on when we look at these bluish nebulas. What happens?
Blue.
Well, there's some in there, right?
The brightest white things are actually blue. Yeah, that's what I'm talking about. And when you see the blue, all right, that's a process where it's a lot of very fine dust. And this fine dust is very good at scattering some of the spectrum from those young stars. And the parts they scatter the best are the blue light in the spectrum. Okay. So this is actually something that cold, dark dust will do. And it doesn't have anything to do with the high temperature. It has to do with a process called scattering. There's only a certain number of colors that the universe has to play with. And you'll see blue in a variety of ways. You'll see red for a variety of reasons. Okay. Same way. So that's why ionized hydrogen will glow red. Okay. But scattered starlight in a cold, dark cloud will be blue, because the blue light from the stars, what's actually being scattered in all directions. That's the same reason that the sky is blue.
No, I was wondering. Yeah, I swear to God, I was thinking, is that, but that's not dust reflecting, scattering off our atmosphere, is it?
Like the sunsets are, kind of.
Well, the sunsets are red because more blue light is being extracted from the sunlight, because it's going across the earth, over the curve of the earth, and more light is being taken out as it crosses that thicker, lengthier amount of air. Okay.
So the color we see because of the curve, it's not the color or ionization or.
Well, no, we have the air molecules, right? We have nitrogen, we have oxygen. Okay. And they scatter, along with dust in the atmosphere, will scatter the blue light very efficiently. Okay. And it's not the only thing that scatters blue light. Tiny, tiny dust particles in a nebula, like this one we just saw, will also scatter the light. And that scattering, again, looks blue because the higher energy light is the most easily disrupted from its original path trying to come to your eye. So it'll get kicked out and sent in all directions. That's why the sky looks blue everywhere you look. Because everywhere you look, the atoms in the atmosphere are scattering blue light in every which way. And because there's so many atoms, you get so many directions, it amounts to being everywhere.
Like the universe is everywhere, the same everywhere you look.
Okay, I'll run with that.
I mean, that's kind of odd. I wonder if there's a connection.
Maybe. I mean, but that's the thing. See, so when we look at a nebula like this, okay, we see the red emission from hydrogen, and we see the blue. It shows, like I said, it shows white here.
Maybe it's just so red it doesn't look blue to my eyes anyway.
Well, the part that's blue in here are those...
On the right. It looks a little bluish, a little
Yeah,
light pale blue.
Yeah, and that's correct. And the one on the right is surrounded by dark, so it's hard to see. But if you look on the one on the left, just above the brightest section to the upper right of it, you can see it's a little blue in there.
Yeah, it's like those optical illusions. Like, are these two the same color? And you say no, one's white and one's blue, and then you take the right away, and they're the exact same. You know,
that's right.
Well,
that's right.
To that point, Amanda, the optical illusion of that dust cloud in there, Mark. So you have that dark dust cloud on the upper right of that image. To me, I used to look at objects like that and think that dark was behind that red.
Yeah.
You know, versus it being in front of it, like you've explained to us. So
yeah, that's something that you're absolutely right. That's something that people have a hard time with. And it's like, especially looking at this image before, let's pull that one in. Okay. You see the Orion Nebula down below, and this is a very, very deep exposure amounting to like 40 seconds. Okay. And you have the Running Man at the top, but in between them, you see that looks like clouds of brown.
It's empty space.
It looks like to the untrained eye, that looks like a void, an area where there's nothing. But in fact, it's dark dust that's obscuring the rest of the nebula behind.
Wow.
Now, is that a limitation to the human eye? Because I'm looking at this like it's a painting. Like, the black is the canvas, the stars are next, then the white, and then the brown and red on top, like as if it's like two-dimensional, like a picture. But it's not, because you could like go around all of this stuff in space, right? So like, is that a limitation of our brain, of our eyes? Is it just because I'm not used to looking at it because I'm not an astronomer? Like, why do I see this as a picture rather than like walking around the house? Like, I can walk around a table, you know what I mean?
I do. And it's a limitation to your eyes because you see what looks like a 2D plane. All right. When you look at the night sky, it looks like it's just flat in front of you. Okay. What you don't realize, but you do now. I know you do, Amanda, and Tara does. Okay. What you do realize now,
the Earth is flat.
It's 3D. The Earth is flat. Yeah.
My brain is flat after this show.
Yeah. As long as you just like deflate.
Yeah.
No.
Sorry. Go ahead.
The whole universe is 3-dimensional, right? So when you look at things like, okay, let's take this right here. The nebula at the bottom is behind the brown dust just above. Okay. And the Running Man Nebula above all that is behind the dark nebula as well. And that's like a bar from the lower left to the upper right of dark material that is in front of this brighter nebula.
Very cool.
And if you look to the far left, you have what looks like a finger sticking in to the image. And that is brown material, brown dust. Okay. But again, it's all 3-dimensional. So behind that little finger is more darker dust. Okay. And you can actually see it. You can see how it's darker dust behind that. So that shows you that even that dark stuff is layered in layers of density and depth. And it's just the most incredible thing. And when we take the pictures with the observatory, it becomes very, very clear. We see that, and again, this dark dust is throughout the universe. We know where it comes from. It came from countless supernova explosions. It came from stars making carbon compounds in their outer atmospheres as they got older. These are called carbon stars. We've looked at those before. And the carbon stars have this beautiful blood red color, and they're just unearthly. They just look unearthly, Yeah. And here's another one. Okay, here's another one. In here, the Orion Nebula is at the top, and down below it, what's it look like?
It looks like a drain almost.
I guess it does. Yeah. And down below, you see this brown cloud of dust, and then just below center and to the left, you see a little blue patch, and that's a reflection nebula. It's behind the brown dust.
Wow.
And then you see a brighter patch below those two little blue patches, and that's actually a bright nebula called NGC 1999. That's New General Catalog Designation 1999. And it's also known as the Rubber Stamp Nebula, and everything's a little tiny black spot in it, which is kind of cool. And that little brown bar of material just above that bright spot is occluding or hiding the bluish nebula behind it, of which the thing there, that white blob, is part of, or even creates. See? And that blue stuff in the background is just being hidden by this dust, which is in front of all of it. See, I mean, this is very cool stuff. And
so I have a question to that. So doesn't the James Webb, now how does the James Webb see differently than what you're seeing? And can it identify exactly which stars are causing the reflections? Could it?
Yes, it can, and it does. And that's sort of like the main topic for tonight that we're going to talk about too.
Oh,
because
good.
No, you're absolutely right. No, but that's a very good question, because the James Webb doesn't see with the light like we see with our eyes. Just to give you an idea, our eyes see in the range of 0.3 or 0.4 microns to about 0.7 microns. What the heck is that? It's a measurement. It's a measurement. It's a size. Okay. Otherwise, you can also say 400 nanometers to 700 nanometers. Okay.
That makes sense.
So yeah, right. A nanometer is a billionth of a meter. So you can see we're talking about tiny frequencies of light. But the James Webb Telescope is looking in the thousands of nanometer settings, way, way out. Wow. So when you have, if our visible spectrum goes from, say, 400 nanometers to 700 nanometers in size, right? That's everything you see is in this little scope. The James Webb is way out here, looking out here, and stuff that's not even visible in my camera view. Okay. And so when you look out that far, you're seeing infrared, which is heat. Okay. Simply, it's heat. So you can see young stars that haven't even winked on yet. We're going to see one. Okay. Well, you can see all kinds of things.
Is it heat or is it light?
Light is heat. Heat is light.
Love is love.
Hey, love. Yes, of course. Yes. Heat is light and light is heat. Okay. I know it's hard to believe, but it's just part of the spectrum you can't see with your eye. It's very red light. So red that you can't see the color anymore with your receptors in your eyes. But with an infrared camera, you can certainly see what you look like in the infrared, and you look very, very different in the infrared.
I don't want to see.
I'm not very pleasant looking in the infrared.
It would be interesting to see, though.
Yeah, well, I have an infrared. I have an infrared system right here that we could use at some point. I have another one on the drone. Okay, works differently. But the point is, infrared light allows you to see things that your eyes can't see, right? Because it's taking that invisible light and bringing it into the visible region and showing you what it looks like. Okay, so in the same way, the James Webb won't just be looking at things like this. It's also looking at things like this. This is the Messier 33, or the Triangulum galaxy. If you notice in that Triangulum galaxy there, you'll see some dark lanes, dark spots that travel along the spiral arms. Those right there, those are exactly what we're talking about. Those are the same thing as this dark dust that you see, that black dust there. It's the same thing as this dust here, okay, just in another galaxy. So in other words, all galaxies have the same kind of, not all, but most galaxies have the same kind of processes going on. We see bright emission nebulas like the ones we just saw. We see dark regions of dust like the ones we just saw. It goes on and on. And this is something that we just can't avoid questioning and wondering about, right? And all the way back to the first astronomers wondering what that blob in the sky was in the Andromeda constellation, right? Turned out that it wasn't until Edwin Hubble came along that they actually started to theorize that maybe these things are separate objects that don't belong in our galaxy. And when they finally figured it out, he figured out that these objects demonstrate characteristics that show they're not in our galaxy. Then we start finding other galaxies. The Andromeda galaxy is that big in the sky. I mean, it's huge, like 3 or so degrees or more. And there's another galaxy right near it. And that other galaxy is the one we just saw, this one. Okay. We've taken dozens of pictures of all of these things that I've just showed you. And they're all available, like I said, for free. You can go check them out in our database. Again, go to skythrowlive.com right there on the bottom and check us out and see exactly what it is we do. Right.
I feel like one of those primitive people you're talking about before Hubble. Like, still to this, I don't know how long I've been hanging out trying to learn this stuff. And to this day, even just now, when you're talking about other galaxies, it still sounds so made up to me. It sounds like you're talking about the latest Star Wars movie. Or like, you know what I mean? Like far-fetched, like, let's go visit the next galaxy and see, like Star Trek or something, like going to these distant galaxies. It sounds like something out of Lord of the Rings. It sounds like, you know, made up, like, but there are other galaxies out there. Like, there are other
billions
exoplanets
of them
out there. Like, I mean, you said there's more exoplanets than stars. And whose theory was that? Like, if there's that many stars, why isn't it constantly light out?
Oh, that's Olbers. That's Olbers paradox.
You know, like things like that. Like, that's a good question. That's a good question. And you can explain it, you know, as many times as you want, but like, it's still hard to wrap my head around. Like, the universe being 3D, like these, looking at these as if they're paintings, but knowing they're not. Like, I cannot wrap my head around any of this. Like, it's so, the universe is so big, and then you're talking about like nanometers and like, you know, like, and it's so small, like that Power of 100 video, and it's on YouTube. Check out the Power of 100. Or the Power of 10, right?
Power of 10, yeah,
10, and it goes back and back, and like, I just people are just like, it's like that quantum leap or whatever, where like everyone thinks the world is flat, and then one person out of nowhere is like, you know what? I don't think so, and they follow it and they prove it, and then everyone else is like, how could we have not seen this? Like, it's just a thing, but then people today still can't wrap their head around it. Like, I don't know, that it's an exciting show, and I'm glad we have it, because it's, people need to know this. It's crazy, and it changes everything.
And that's kind of what I was thinking, if I can, real quick, Mark, and then you can reply, because part of that is, it's hard to believe because it does look two-dimensional, but that James Webb, the infrared, that'll help us see the 3D more, right? Does that help, Mark?
Because the way the James Webb telescope is going to work, or does work, is it sees in the infrared. What that means is, let's pick an object. Let's go back to this one. Okay, see that dark dust right there in the bottom left, basically. Okay, that's actually gets opaque at some point, so we can't see the stars through it. Now, stars are very bright, but this dust, enough of this dust, can obscure stars behind it. And those are stars that we will never see unless we use a different process. And that process is the use of the infrared telescopes on the James Webb. The infrared telescopes see through the dust. They see the heat coming from inside the dust, and we'll see specific blobs of objects, okay, including stars before they're born. I have one to show you later. We have one here that James Webb found, a star before it's actually born.
How can that be?
It's called a protostar.
Oh.
Actually, Ronald had a question. I don't know if this is what you're going to be talking about or not. Let's see. So what galaxy do we see a supernova occur? That's not what you're talking about now.
No, but that's okay, but a supernova, of course, is when a star runs out of its final fusion reactants, and it just suddenly collapses because gravity wins over the outward pressure of the radiation that's trying to hold the star up, and manages to make it, you know, stay in this equilibrium for, in the case of a big star, millions of years as opposed to billions. And eventually, when all that outward material flowing outward, that radiation flowing outward to hold the star up, falls away, it's like opening the nozzle of a balloon. It's gonna collapse. Well, it's just, and
there goes the planet.
And look at the stars go across the universe. Wow! Hey, mommy, a supernova. No, cool. But as what happens though is, because the star is out in space, the collapse is uniform on all sides, and it collapses. And so the core of the star collapses, and the star, of course, can't handle that, and it blows itself to smithereens, and that's the process we call a supernova. And when it does that, it returns all of those amazing ingredients that it concocted in its core, okay, back to the universe. And those go back to creating the elements that we see in our periodic table. You, every one of you, are made of material that was once formed in millions and even billions of degrees of temperature in the heart of a star at one point. Isn't that crazy just to think about?
Guys, give me the lyric.
We are Stardust.
Perfect. Yeah. Okay, chat, game over.
That's it. That was easy.
Now, and I might, again, I'm probably confusing things, but is this what's going to happen to Betelgeuse?
No, you're not confusing it at all, Amanda. That's exactly correct.
Is Betelgeuse a star? I was thinking it's not a star, it's something else. And
Is
this
it Betelgeuse?
Don't say it. Yeah, don't say it 3 times.
Oh.
Yes, or else Michael Keaton will go, "Hey, I'm somebody now," you know. But
oh, come on!
I love that show. It was a good
like
movie.
Michael Keaton.
Yeah, Beetlejuice was a good movie.
That's it. 3rd time.
No, you gotta say it 3. You gotta say Beetlejuice, Beetlejuice, Beetlejuice. Oh no. Oh yeah, we have to.
We have a Betelgeuse nebula, don't we?
No, we have a. Well, okay. Let's take a step back, because technically no, but yes, and I'll tell you why your answer is both wrong and correct.
I'm so confused.
I know.
One question at a time. Sorry.
No, that's good. Okay, you asked about Betelgeuse. What will happen with Betelgeuse? Okay, Betelgeuse is 750 light years away, so it is in the end stages of its life. It's on the final track. All right, it's eventually going to go supernova. When it finally runs out of all those nuclear fuels I was talking about, its core is going to collapse. That core is going to bounce off the iron in the core and shoot outward at high speed. Meanwhile, the rest of the star is already collapsing. So as it's coming, all this stuff is collapsing. All this other stuff is racing out. And I didn't mention that before, but that's how a supernova sort of works. And then the star gets ripped to pieces in that case. And we'll see that. But at 750 light years away, we're seeing it as it was 750 years ago. Right. So if Betelgeuse goes supernova, if it happens right now today, we won't know about it for 750 years. Okay. And if it went 749.999 years ago, then we should go out later on tonight and watch. You see what I mean? Yeah. We don't know. So the thing is, when Betelgeuse goes off, 2 things are going to happen. First of all, you're going to see it in the daytime sky like another star. Not nearly as bright as our sun, but kind of like a planet.
Wow.
Like Venus? Would it be brighter than Venus?
It might be just about the brightness of Venus.
Cool.
Okay. And then it'll be that way for several months, most likely. And then as that final burst of radiation from the supernova starts to wane and dissipate, the temperature will drop, and we'll actually watch the temperature drop itself. We did this with a supernova in a galaxy with Skytra livestream. We watched the galaxy. I think the galaxy was called M64 or M66. I can't remember. And we kept going back, whatever it was. Yeah. We kept going back, and we looked at it night after night, a few nights in a row, and then over a period of 3 months. And at the very beginning, it was a bright blue dot in this galaxy. Now, blue is, of course, hot, very high frequency light. This is the initial explosion of the supernova. By the end of 3 months, that object, for the same exposure time and everything, was now red, indicating the temperature had dropped significantly. And we caught that. We caught that change.
I wonder if that's what Ronald was talking about, one that you specifically saw, that he would have watched.
Oh, that Ronald, you might have been right. It might have been that one, because we did see it many times, and we showed it and we talked about it. We explained how supernovae work. It was great.
I bet that's what it was then. Yeah. It seemed like he was talking about a specific thing that you would have known about or seen or showed or something. So I bet that was it. Hope that answers your question, Ronald.
Yeah, well, there's a lot of people asking questions out there, so.
Now, would this explosion be big enough to affect because that is what the kind of first, and again, I know it's 3-dimensional, but if we're looking at Orion, it would be the leftist most star in the 3 of his belt, right?
No. Betelgeuse is the orange one in the upper left.
In the corner. His
Did I not
shoulders,
say left?
right?
It's in the upper left of Orion. The belt
it would be
of
the
3,
first one, then a middle, and then the one on the right. It's the most left, no?
No, the Betelgeuse is not in the belt of Orion. Betelgeuse is one of those outer 4 stars. The belt.
Oh, I thought it was in the belt. Okay, never mind.
No,
okay.
But that's good to clarify. Thank you.
Mm-hmm.
Betelgeuse is the upper left star in Orion, and it looks orange to us now, but it didn't always look orange. Okay, back when Betelgeuse was a young star, and that was only like 10 million years ago or so. I mean, it might have been even less, maybe 4.
Little grasshopper, yeah.
Yeah. But see, that sounds like a long time to us, but that's a very short lifetime for a star, seeing that our sun goes 10 billion years in length. And that some of these red dwarf stars, little tiny red stars, these little percolators in the universe that I call them, they can last trillions of years. In fact,
trillions.
The first M star that was ever made in the universe is still out there today and has not destroyed itself.
And we know that how?
Because we know how red stars like this evolve, and these tiny little red stars use so little energy. Well, they're using, obviously, putting out lots of energy, but they're actually mixing their outer contents of hydrogen gas back into the center, and that's being used to do hydrogen fusion forever and ever and ever.
Wow.
Effectively, it's trillions of years of life for these little red stars. They'll be the last thing to go in our universe. Okay, they'll outlast the sun. In fact, the first star that ever became a red dwarf star will probably outlast our sun.
Wow.
And that was 13.8 billion years ago. These stars last trillions of years.
Trillions.
And we last
amazing.
We last 10 billion years with the sun. So first.
Now, I was worried. I thought it was in his belt, and my next question was going to be, does that mean Orion's pants are going to fall down?
That's a good question.
His suspenders might fall down.
No, it's just his shoulder's going to get blown off. That's all.
Oh, God.
And he won't be able to hold the club anymore. The thing about Betelgeuse, though, is interesting because it went from being a hot blue star to being a red supergiant as it is now, because that it was hot and blue when it was younger, and then it swelled into this red giant as it went through this phase. It goes to a red giant once, and then it begins to contract again, and then it starts to fuse helium, in which case it's a brand new life called the horizontal branch. It's a part of the Hertzsprung-Russell diagram, Amanda. You may remember that diagram that we had. I don't know.
We had it.
Here it is, right there.
Yeah.
Okay, that's the Hertzsprung-Russell diagram. Betelgeuse is up there in the upper right. That's where it is. But it used to be on the left in the blue area. Okay, so it was a very, very hot young star, went up into this supergiant phase, and it's eventually going to exhaust all of its final fuels, and then it's going to go supernova. Now, the thing about that is it serves, it actually will offer no danger to us whatsoever. At 750 light years away, we can just sit there with our lawn chairs and enjoy the show. Okay.
Not even get a suntan?
No, you won't even get a suntan. I mean, you have a better chance of getting a suntan from Jupiter's reflected light than from Betelgeuse. So not to worry. But you will see it in the daytime. Will see it cool. That's going to be good. I can't wait. I mean, I only have anywhere up to 10,000 years to wait, right?
Rocket said that it was going to outshine the moon. We were looking for comparisons of what it might look like in the daytime. So
yeah, but remember, it's not going to be anywhere near the size of the moon. Okay,
little tiny. Right?
The moon's a half a degree in space, and unfortunately, Betelgeuse is going to be a tiny little point-like object in the sky, but just very bright. Right. Kind of like Venus looks, but Venus has actually got an angular dimension. It's got a real size in the sky because it's a planet. You could see it as a planet when you look at it with a telescope. Right. Betelgeuse, you won't be able to see that. It's still going to be a point source, so it might be affected by the what do you call atmospheric scintillation. The turbulence of the air might make it its image dance around a lot like this. Look at my image dancing around. Okay, but you're not going to have a problem with it causing any problem or damage to the Earth whatsoever. I can't wait. I would love to see this happen. What can I say?
I wonder, but how many people, like on average, how many people do you think are aware of this? I would say not many. Like on the grand scheme of things, how many people are going to freak out? because they'll have no. I mean, the average person is not. I wouldn't have known if you didn't tell me. I would not have known.
She's right, Tara.
It's War of the Worlds all over again.
People
right?
are going to freak out. If you don't know what this is, that's going to be terrifying. Tell me I'm wrong.
Yeah, no, you're not.
So we will be evolved.
We come in peace. We come in peace.
And you said this could have happened theoretically 749 years ago, and we wouldn't know. So it's not like we can say, okay, in the next 6 months, expect to see this disturbance in the sky and warn people. You know, like, and then after the fact, like, there's so much, you know, conspiracy out there. Oh, it's Betelgeuse didn't explode. This is some kind of, you know, invasion or government technology or World War III setting nukes off in space. Like, people, if they don't know that this is going to happen, telling them after the fact will seem like a cover-up. Like, people are going to freak out.
Yeah,
well, you can't either way. People are going to be talking about it. Which direction?
That's right. And meanwhile, they'll be talking about the end of the world, right? And I know we only have like a minute before we have to go to break, but
it's almost the end of the world.
It's almost the end of our world. Yeah, but
get yourself
end of the segment. It's scary enough.
It's like 2 minutes. Get your beep together. Okay. No, but when Betelgeuse does go supernova, one of the things it's going to do, and you asked about whether it was a nebula. And I have to just be careful with that answer because Betelgeuse has been losing mass. It's called mass loss. Big stars go through this. And it does have clouds of dust around it that it made in its outer atmosphere. It's so big that the outer atmosphere is not so hot that it's going to make everything into plasma, which is just protons and electrons zooming around. Okay. Right. You still have atoms out there, and you can actually get molecules of stuff. Okay, this is a dust particle. This is an interstellar, a real piece of interstellar dust that was captured by a spacecraft, brought back to Earth. Okay, that is the kind of stuff that gets made in the outer atmosphere of the red giant, and it congeals and it makes more and more and more of these particles connect until they make something like this thing. Okay,
it's so organic looking.
It is, so that's how that works. But, I think we'll have more to talk about when we get back, and we have to dive into the James Webb stuff because this stuff is really, really cool. Mm-hmm. So I hope you guys enjoyed this and stick with us, but we'll be right back after this break. All right. So don't go away.
Hey members, the new KGRA DB app is now available on iOS and Android devices. Gain on-demand access to any KGRA DB programming. Download any show directly to your mobile device to listen or watch on the go. Go to the App Store and search KGRA DB.
Are you looking to go on a faraway journey that is magical and mysterious, reaping on mystical legends? If so, then Mysterious Adventure Tours is perfect for you. Imagine a voyage to explore ancient mysteries of Ireland, haunted majesties of Scotland, or their chilling Birth of the Vampires in Romania. These small, esoteric getaways are limited and do fill fast. So, go to MysteriousAdventuretours.com and book your trip soon.
You're listening to the KGRA Digital Broadcasting Network. We provide unparalleled coverage of trending news in the world of ufology, cryptozoology, and paranormal phenomenon. Whether you're watching our video live stream or listening to one of our audio programs, you are getting the best from world-renowned researchers and hosts, guiding you through topics the mainstream won't touch. Miss one of your favorite programs? No problem. Head over to the members area at kgradb.com for access to our massive library of award-winning content. Make contact, stay connected. only at kgradb.com.
Welcome back. Welcome back. It is I, Mark D'Antonio. At least I think I am. Yep, I'm me. Oh, Tara over there. Hi, Tara.
Hi.
And Amanda joined us down there. It's nice to see you. Daryl has a night off. I want to say thank you guys for coming out here. This is a lot of fun. And to you guys listening out there, it's a pleasure to have you with us. We have been talking about a variety of things in the first half. But now I want to get into talking about some of the topics that we kind of touched upon when we talked about infrared technology and how that all works.
Cool.
Yeah. And Tara, you kind of brought this up earlier when you started talking about infrared and how it actually works. And the James Webb Space Telescope, affectionately known as Webby, okay, or JWST.
What's those friends call him?
His friends call him Webby, right?
Yeah.
Yeah. Hey there, hi, how you doing? Yeah. Hey, come here, check this out. Look at this thing. Okay. I'll show it to you in ways you've never seen before, Yeah. And the Webb telescope has shown us things that are absolutely amazing. And the Webb telescope has made a true discovery. And that discovery has to do with a star called LHS 475.
Of course.
Right. I mean, a very romantic name and very telling name. LHS 475. It's like, wow.
What's it telling us?
What's it telling us, right? Yeah. Well, LHS 475 is one of these M-type stars. And when Amanda mentioned the OBAF GKM, temperature scale and or spectral class scale that we talk about, where and she would tell you it's the O stars are the hottest and the bluest, and the M stars are the coolest and the reddest, and that's true. Well, the coolest and the reddest stars are those ones I talked about, which will last trillions of years. So they might have a chance to foster potential life, right?
Cool.
Because they're going to have trillions of years to stabilize. They're known as flare stars. They actually give off a lot of ultraviolet energy sometimes for all their coolness. But this particular one, LHS 475, is in the constellation of Octans, Octans. Octans is the southern hemisphere, southernmost South Pole constellation.
Wow.
We can't see it from here. Okay. But Octans has a star in it that's one of these M-type stars. I mean, the M-type stars are the most common star in the entire universe. So there's more of those than any other kind, and they have more planets around them than any other type of star. Okay. So this star is known as an M3.5. Okay. That means it's on an M0 to M9, it's a 3.5. So it's a little bit on the warmer end of the M stars, which are not very hot. And so that puts it as a fairly warm M-type star. And it's also fusing hydrogen into helium like our sun is doing. But it makes sense that it's doing that because every M star we know about, almost every M star is one of those types of stars. They haven't stopped fusing hydrogen into helium. Okay. So this is an M3.5 dwarf, as they're called. But don't let that mean to you that it's a small star, okay? Because our sun is also a dwarf. Compared to Betelgeuse, it's a dwarf. I can tell you that because you put Betelgeuse where the sun is, it would go out and reach Jupiter's orbit 5 astronomical units away. So we'd actually have a star that's 10 astronomical units in diameter, double that. That's a big star.
It's contrary.
It's contrary to it. And it's the kind of thing that Amanda would say is basically, like a
doesn't make sense.
Fairy tale. Doesn't sound like it's even real, right?
Well, you know what I mean.
Yeah,
I know it's
true.
real. I'm not denying
it
anything,
is.
but
no, you're right.
But there's these
fantastical ideas, and we. I mean, with James Webb, we're just now trying to prove some of these theories that have been around for who knows how long. So it's, you can't really, I don't know. I guess it's all theory until you prove it, right? And
Mm-hmm.
they're great ideas, but like, I think it was in my lifetime that it was proved that the atom was not the smallest thing in the world, in the universe. Like, that's when I was little, it was. I mean, when I was little, Pluto was a planet. So, I mean, like, things change and things evolve, and no matter how close you think you are, you're never going to know. You can have a million theories and fractions of each could be right, but that's why I think everyone should be sharing this information and, rather than, ooh, I have a secret on a big discovery that I'm never going to tell and be famous. Well, then you try and no one ever knows, like.
Yeah. Well, the James Webb's going to make those big discoveries possibly, right? That makes everybody know and changes things.
Yeah, it already has. I mean, it's the James Webb has the capability of not just looking for exoplanets like the transiting exoplanet survey satellite known as TESS did, or the Kepler Space Telescope did, and then the follow-on to Kepler using the same platform called K2, where they actually modified the original Kepler to live a little longer. Okay, and out of those, we got like 5,000 exoplanets, and the candidate number is gone way higher now because of all this, and the James Webb is finding them itself. But the James Webb has an additional trick up its sleeve. It can see if these planets have atmospheres, and it can tell you what's in them.
Ooh, ta-da!
That is a ta-da. We're gonna see that in a little bit from now. I'm going to show you some of the imagery showing you what we've discovered in some of these exoplanet atmospheres.
Oh,
and
cool.
it might be pretty shocking to some of you. No, it's not little green men going, "Hi there, we're here. Hey, quit looking at me. I'm not getting any clothes on." I mean, that's not gonna be anything like that.
Be like oxygen signature type stuff, or
signatures of materials and chemicals that we think are important. Now
for our life.
Yeah, for our life. That's right. As carbon-based beings, okay, and we'll see that in just a few minutes. But the star that is the one that the James Webb looked at, this LHS 475. It is one of these small dwarfs. It's actually 2/10 the size of our sun and 2/10 the size of the mass.
That's tiny.
It's a tiny guy. Yeah, it is, and it's 41 light years from Earth. Okay, 40.7. Okay,
kind of close.
Yeah, kind of close. Actually, very close for considering how how far distances are in the universe. That's actually considered close. That's considered our neighborhood. Okay, that's our solar neighborhood. But stars like this, one of the reasons why they're so flamboyantly copious with their ultraviolet flares is because we talked about stars and big stars before and small stars, but a star has this radiation giving off in the center, right? And all stars have that, but they also have an outer layer that's convective. It's like a pot that's boiling, okay?
Oh.
And for these red stars, that convection zone reaches all the way to that radiative core. So the whole star is one big boiling pot of water, basically.
Wow.
But not water, right? It's a boiling plasma of hydrogen gas mostly. So that's why these stars live so long. They get to use all their hydrogen, whereas our sun only has the hydrogen near the core that it can translate into helium. Okay, that stuff on the outside is also hydrogen, but it can never get in there. It's not going down to the depth where it can be taken into the core. None of that's happening. So stars, when they're fusing this material, it's only happening in the core. Okay, only happening in the core, and the outer layers are just along for the ride. Okay, that's how stars work. So interestingly, our sun has a small core, and these M stars have a smaller core, but they have these big boiling pot processes. There's these convective layers that go all the way down to the core and circulate hydrogen down into the core that can be used for fusion in these little red stars. That's why they live so long, because they have a lot of hydrogen to use, right?
It's the fountain of youth.
it basically, yeah. So now the other thing too is when we talk about these small stars being so small, again, 0.2 times the size of our sun, that means that the zone where life can live, what we call the habitable zone, is going to be a lot closer to the star. And many of these red stars have a habitable zone that is just very, very close to the star. Now, we gauge a year on Earth by how long it takes the Earth to go around the sun.
Right.
365 days. For some of these red stars, a year, for the smallest year we've discovered on one of these red stars, because the planets are so close, a year is 4 hours. In 4 hours, It goes around the star one time. Now, that's not a planet in the habitable zone, okay? But that's a planet circling the star once every 4 hours.
That's fast.
Well, doesn't Mercury take like 82 days? And that's definitely not habitable. So something taking 4 hours a year, like that's, I mean, how does that even exist?
Well, keep in mind that the stars are much, much cooler than our sun. So the zone of livability where you could live is much, much closer to the star. Okay.
Right.
So I'll give you an example. TRAPPIST-1.
Shorter trip.
You might have remembered TRAPPIST-1. We talked about TRAPPIST-1. Amanda, I think you were with us on that show. TRAPPIST-1 is a star system that has 7 planets surrounding its red star. 3 of those planets are in the habitable zone of the star. Okay, I think it's like E, F, and G, or F, G, and H. Okay, and the thing is, the farthest most planet in there has a time to go around the star of 13 days or so.
Oh my goodness!
And Mercury's orbit is way bigger than that from there. Okay, yet 3 of those planets are in the habitable zone for that star. So you see, it's all a matter of perspective and the amount of energy that's given out by the star. If the star is not that energetic, then the planets can be a lot closer and still be in what's called the habitable zone. Follow?
Yeah.
Yeah.
So would you live a longer life if you went around faster? Could you say it's kind of interesting.
Yeah, you could say you could go to this particular star or a particular star. Yeah, thank you, Michael. Yeah, whoa, yeah. You could go to a particular star that has a 4-hour daytime or year-long cycle, stay there for 10 days and say, I went there for 10 years.
Yeah.
It's time.
Now, what effect would that have on your body? Is this like, from our point of view here on Earth, like what would that do if you were on that planet for 4 hours?
Well, for 4 hours, you would be on that planet for 4 hours. Okay. And, for you, it would be 300. It'd be comparable to the year of that planet. Now, you could say, I went there for a year. What you're not telling them is a year is only 4 days on that planet, or 4 hours on that planet. Okay. So if you stayed there for a full day, then you could be there for 2 years. For 8 hours, right?
But what would it do to your body? Would it just
would you have to hold
like
on?
a 4-hour change and you don't see anything? Or I guess if like you were born on that planet, you wouldn't be, an average of like 5'8" or whatever. You'd be like really tall and thin, maybe because of gravity, or just maybe like really, really wide because of the spin. I don't know. I don't know the science of how that would work, but
that's a very good point, though. See, and a lot of people like myself do speculate what intelligent life, if it were to evolve on such a planet, might actually look like, Amanda. And people report gray aliens here on Earth. They're kind of gray with these big almond-shaped eyes, right? And they're black typically. Now, we don't know if those are some type of
lenses or
biological environmental suit, or we don't know that. Okay, but we do know that if you lived on an M star world, you would certainly have a much faster year cycle. In fact, you might not use years for you. You might invent something different. Okay, but you might also be on a planet that is sort of like Earth, so the gravity might be similar, and it can be. Let's say it is. Okay. And the atmosphere might be somewhat breathable. Okay. Maybe it is. Okay. So what would that do to you? Well, if the planet was like the Earth, then you'd probably evolve to be approximately our height. Maybe if you evolved to be a bipedal, upright walking creature. But because the star's light is very red, you might not be sensitive to green and blue as much from your evolution. So your eyes might not see the same way if you develop eyes at all.
Yeah, who knows?
Right. So you might not see the
saying
same way.
Intelligent life. What about like the landscape though? Like if you had a picture of like if you painted a picture of a mountain or something and then like wiped your hand across it like a smear, like the wind like was wiping it away, like something you'd see in a movie or something, like if it's going that fast, would things be like wider and kind of wispier, or?
Well, you wouldn't feel it, because wouldn't it be like here on Earth? We don't feel like we're going at 15,000 miles an hour, however much that is. You know?
Yeah, I mean we're rotating at the equator by about 1,000 miles an hour. We're spinning by 1,000 miles an hour. You certainly don't feel that because you're here. You're on it.
Okay, so well, just because the planet is taking 4 hours to go around its star or whatever, doesn't mean it's spinning faster, right? It could spin the same as Earth, only.
Well, there's a caveat, though, Amanda.
Of course there is.
I know, right? And that is that planets that are around these M stars, remember what I said? The habitable zone is much closer. So the planet is much closer. In all likelihood, those planets are going to be tidally locked to the star. What's that mean? If you recall,
our moon is to Earth.
Very good. Exactly. Like our moon is to the Earth. They'll have the same face pointing at the star. So what's that mean? It means that if you want to go on a tropical vacation, go to the sunny side. Hey, let's go there for 4 hours. That's a whole year. Okay. If that's, it's going to be more like 7, 12, 13 days. It would be something like that in a real situation. 4 hours is extremely close, not habitable. Okay. Around these stars. But, and at the terminator where it's perpetual sunset, that's just stunning. I mean, you could just hop in your car, drive 2 hours further and see the night sky. And that's all you see is the stars. I have a feeling though that, well, as I said before, real estate agents, they get a hold of this. See the tropics, see the sunsets, see the night sky. Okay. You get all three in one shot and you don't have to worry. It's going to just be right there moving over your head. So if you had a 7-day year around some planet, you could literally go there for a week on the night side and watch the entire year of stars go by. So we have to wait until winter to see Orion, right? Well, here at this, when you go to another planet, we wouldn't have to wait till winter. We just have to wait a couple days, right, to see our seasons. Cool. Yeah, yeah. So planets that are tidally locked have their own problems. There might not be habitability at the very, very sunny locations at the very front of the planet that's facing the star, because there might be too much radiation striking the planet from the star. The star will be known to be giving off ultraviolet flares. So maybe there'll be a band around the planet where it's always sunset, kind of a little day, a little night. So maybe there in a band, you would find some life, which means it sounds like a good science fiction. It sounds like a good
book or something.
A good book, yeah. Like Strike Up the Band. And it's all about the band world, right? The world of just the band of M planets. I mean, that'd be kind of cool. And for prison, right? For bad people, they just stick them out on the sunny side in a prison. Go ahead, escape. Where are you gonna go? You'll get baked before you get baked before you get to the Terminator. So yeah, so there's a lot of interesting possibilities, but those stars are fantastic. Now I'll show you. This is actually the light curve for LHS 475 B. Okay, this you see that dip? That's actually the light curve that James Webb captured. And it shows that light curve, the shape of that curve gives us lots and lots of data. Okay. And so when we look there, by examining the depth of this curve, we learn a bunch of things. We can learn about the radius of this planet. Okay. All right. We can learn about its distance from its star. We can learn, again, thanks to the James Webb, we can learn about the composition of its atmosphere. All right. And that's really cool as well. And the composition of the atmosphere comes from the instruments on the James Webb, which we'll talk about in a minute. Now, if we want to know about the mass, like how much mass it has, like the mass of the Earth versus the mass of the moon, right? We know the difference, right? But the mass of the planet comes from another quality called the radial velocity. So what it means is, as a star has a planet orbiting it, as the planet is orbiting the star, the planet tugs on the star just a little bit and moves it around. So you'll see this going on with the star just a little bit as it's being tugged by the planet. I removed it for clarity here. But let's assume that the planet's coming around this way and we're seeing it in a transit. So it's coming in front and then in back, in front and in back. So the star's going to come a little toward us and a little back, and move back. So as it comes around the front, the star is moving a little bit forward. And then as it goes around the back, stars moves a little backwards. So they're actually doing this little dance. Okay. It's like this. This is highly exaggerated. It's more like this. Okay. Right. Well, that dance that they do gives us data because that star's motion toward the front and toward the back is called radial velocity. We can see that. We can detect it by looking at the spectrum. We can see blue shift where the stuff's coming at us and red shift where it's going away. And so measuring that amount of shift tells us how much mass is tugging on that star, and it will tell us the mass of the planet. Isn't that cool?
Oh, that is really cool.
Yeah. And thanks to the Webb, we have a lot of things. Now, the Webb Space Telescope also looked at another star called AU Microscopy. There's a constellation called Microscopium. And
that's a good one.
Yeah, AU Microscopy is a star here. That star symbol that you see is just the location of the actual star. That dotted line is the glare of the star, and it's the outline of the artificially removed location of the glare from the star. Okay, now these images show this dusty debris disk around AU Microscopy. It's another red dwarf star. It's 32 light years away, and it's in the constellation of, I just said it, Microscopium. Okay?
Oh, that was a trick question.
It was. And it has 2 known planets. Okay, one is 20 times the mass of the Earth, and one is 11 times the mass of the Earth.
Oh, big.
All right. So these are not super Earths. These are definitely much bigger than that. A super Earth is anything larger than the Earth, but smaller than the smallest gas giant in our solar system, which is Uranus. And Uranus is about 14 and a half masses of the Earth. And these, this like the 20, that's right outside, 11 times the mass of the Earth. It's kind of up there, but it might be considered a potential super Earth. Now, saying super Earth doesn't mean it's habitable. It says nothing about whether it's Earth-like. And
or if it's the type of planet, like gas or Earth-like. Is that what you mean?
Yeah, when you say super Earth, we tend to think rocky planet. We don't say it has an atmosphere of like anything we know of or can breathe. And so the word Earth, that should probably be replaced, a super Terran, or super Terra planet, where it's
super
like
Terra.
Yeah, exactly. We call it, well, I was thinking TERRA, but
of course.
We could call it TARA. That's actually, I just thought of that because you said that. That's funny. But this dust disk is interesting because it shows knots of material. But one of the most interesting things, and this goes back to something you had talked about earlier, Amanda, about the blue reflection nebulae. Okay, this is the dust disk that was captured by the Webb. Okay, around the star.
Wow.
Now, why is it blue? Why is it red? Well, okay, the reason that it's blue is because this was a capture at 3.3 or so, 3.5 microns. So this was at 3,560 nanometers, still far in the infrared. So you say, well, why isn't it red? Because they use blue to show that it's actually a shorter wavelength than the red down below. That's all. It's just a false color. Okay, because the red down below is at 4,400 nanometers. It's actually a slightly longer wavelength. And what's interesting is the blue is actually brighter, and that tells us something, because when we look in the blue one, okay, the shorter wavelength means that these particles here are smaller. And it's showing us that most of this dust around this star happens to be these tiny, tiny dust particles, things more akin to, well, let's put it this way. That dust particle I showed you earlier, okay, this guy right here.
Right.
Yeah, that dust particle is way, way too big. It would be considered massive compared to the kind of dust we're talking about here. We're talking about tiny little tiny, tiny little spindles of dust at the very least. Okay, so that's what's interesting about this. So again, the James Webb near infrared cam, NIR, was able to look at this and capture this. Now the coronagraph blocks the star's glare, and the way that works is when you're looking at the sun and it's too bright, what do? You hold your hand up, right? You hold your hand up and you block out the sun, and it allows you to see stuff around the sun. It allows you to see around the sun.
Right.
Well, that's what a coronagraph does. It's like blocking out the stars so you can see what's around it. Okay, so that's actually what the coronagraph it does to allow us to see all this. Otherwise, this would all be lost in the glare. All
well, okay, so what would the true color be? Because these are looking through different lenses for what's around the star. Is that like when you get close enough, is everything just white because it's so bright?
Well, the star is actually a red dwarf, so most likely some of the reflective material is going to look kind of reddish.
Yeah, I heard you say blue is not the true color, but
correct.
So it made me think: does that mean red is, or is it something else? Because we're
well, in this case, the actual color of the grains might actually be kind of a brownish black, maybe maybe gray, a dark gray. That'd be the actual color most likely of these grains, but we're just seeing the heat response here. So they're heated grains, and heated grains to an infrared camera, you never see them in the actual color they are. You just see the relative amount of heat that they're giving off.
And that heat isn't given off in the form of light, correct?
No, it is. All heat is light. Okay.
But it's such a low heat. It's just the cumulative of all the dust particles that we're seeing it so bright. Is that?
Well, when we're seeing this, we're actually seeing what the infrared sensor is detecting. And like, let's look at the orange line down there. That's an orange line of dust around this star. It's called a debris disk. Well, in the infrared, first of all, we couldn't photograph this like we see it with our eyes because we wouldn't be able to see anything. It's too far away, it's too faint. But the infrared energy is much stronger because the star has been heating this material up, and that star's particles around it radiate away this infrared energy. Again, infrared energy is light. It's just light we can't see. And so it's far down past the red end of the spectrum where we see with our eyes. Okay. And this is what we end up seeing. Okay. And this is, it's kind of, the way infrared works is sort of like a godsend to us because it allows us to see the invisible, right? Because just like if you looked at your face with an infrared camera, okay, you'll see that your nose is a hot spot. You'll see your eyes are cooler. You'll see that your area around your mouth has got this hot spot. Your ears are going to be hot spots. Your forehead will be a hot spot. And then the areas here be cooler. You'll look like some kind of monster in the infrared, okay? But that's how that light operates. You're only looking at the heat. Okay. And if those heat signatures are following the contour of something like a face, well, then you can see a face in that infrared light. Otherwise you can't.
That's cool.
Yeah, it is. It's really interesting. So this is cool because the Webb took these images. Again, they're false color. They're just to show a slightly shorter infrared wavelength over a longer infrared wavelength, the shorter one being the blue, the longer one being the red. And the blue is much brighter, which shows that this is something that this dust disk is made of those really, really tiny particles.
Teensies.
Yeah, you got it. Yeah.
So, but if we could see it with our naked eye, it would be the hot dust scattering around it, making it appear red.
That's correct. Okay. In all likelihood. Yeah, and if you shine a white light on this dust, if you brought a flashlight and shined it at it, well, then the dust is probably going to be grayish, black in color, maybe brown in real life. But if all it has is a reddish light to reflect, it's going to look kind of like a shade of red. Mm-hmm. Okay, pretty cool. Now, the Hubble Space Telescope also took an image of this. And just to give you an idea of how big this is, in this image, you can see down below, size of Neptune's orbit. Okay. Now,
Wow.
this disk spans over 60 astronomical units. Okay.
Wow.
That's 5.6 billion miles. That's a huge, huge distance. So for us, that means we're looking at an entire solar system here, because out beyond Neptune's orbit, for us, we have the Kuiper belt, which is that belt of icy objects. The thing about this system, however, is that debris disk that we see actually comes in as close as Jupiter's orbit to our sun. Now, I find that interesting too. So it goes from around Jupiter's orbit on out. Here in our solar system, we have an asteroid belt after Mars and up to Jupiter. Then we have some special, other objects out there a little bit. They're doing their own orbits and things. But then beyond Neptune, we and so forth, we actually have the Kuiper belt, which is the belt of icy objects. Beyond that, we have the Oort belt, which is a belt of more icy objects, and an Oort cloud, which is a spherical debris cloud surrounding our sun, like Pigpen has always got dust around them in Charlie Brown.
He's dropping asteroids and meteors on us, right?
That's right. That's effectively right.
Mm-hmm.
I have a question about that last picture.
Yeah.
On the bottom image, what are those white lines going across? That's got to be Mark's cell phone.
It was, sorry.
Oh my gosh.
What I mean, the vertical ones?
Yeah.
I'm not sure, but I'm imagining those are observation swaths, because the Hubble Space Telescope probably looked at different sections, and I think that might have been the observations done by the Hubble. I'm not sure. Sure.
Okay, I have a question on that image as well. So, Mark, did I hear you say that the accretion disk is a lot closer to that star than what ours is? Is that what you're saying? And is that the news on this?
Well, no, the news, first of all, is this one, that the Webb telescope saw this and actually detected, knots. There's knots in this debris that was never seen before. And that could be indicative of potential planets and so forth.
Oh, cool.
But the Hubble observation that you're seeing here, okay, this entire disk is like I said, it's 60 astronomical units in length. Well, it's actually more than that, and it's, believe it or not, this particular object is also it's, besides that size, the disk itself, if you look at how close it comes to the sun or the star, it comes in as close as Jupiter's orbit. Now, in our solar system, what's odd is closer than Jupiter's orbit, we have an asteroid belt. Right. And then inward, there's no dust disk, with large objects in it. Okay. We have the zodiacal light, which is caused by this residual dust in our solar system that may very well come from the planet Mars, in fact. But that dust is something that an alien civilization could probably see. All right. But this goes in as close as Jupiter is to our sun. All right. So it doesn't come in as close as our asteroid belt is to us. So in that case, but again, it's a small red star. So this is a very odd system to have with a small red star. With a star like our sun, that's hundreds of times bigger. Well, then I would think that, we're talking, or 2 times bigger at least, then we're probably looking at a very extensive debris disk that goes out quite a long distance. It's really quite a fascinating location, So if we have questions, I'll take them, but otherwise I'll move on to the next object here.
Yeah, go for it. Keep going. This is
okay.
Cool.
Well, we did have a few questions. Sam wanted to know if the stars were accreting the dust.
Oh, that's a good one.
Yeah, actually, that's a very good question. Thanks, Sam. Yeah. That star, when it was first formed, and this dust was accreting that dust. Now, it doesn't mean that the star is eating it up or absorbing it and burning it up. It means that it's orbiting the star. So there are cases where dust and planets, in fact, can spiral into the star and be, destroyed. But in general, if a solar system or star system forms, those might be stable orbits. And so that dust may be just orbiting the star. So the word accreting is a little throwing me there, Sam. So the star has an accretion disk, okay, but we call it a debris disk, right? And that's not necessarily something that's going to be destroyed by the star. They could be orbiting it.
Okay, speaking of destruction, Charles has a question.
Charles,
how close to a star of this class would a terrestrial planet start to break up due to tidal force?
That depends incredibly on the mass. I was just going through an exercise today on something called the Roche limit, which is what he's asking about. When a planet gets too close to a star, okay, then the differential gravitational force on the planet's nearest side and the farthest side can rip the planet apart. Give you an example. When you look at Saturn's rings, its Roche lobe, the maximum orbital space for a spherical planet, is just outside of its ring system. Makes sense, doesn't it? Because inside the ring system, there's nothing but fragments and small pieces, right? And ice particles, right? And that's what happens there. So it depends on the size and the mass of the star. I would say, believe it or not, Charles, this is a good question, because I was going to write a program after I did this Roche lobe thing, and thought, I want to actually do a calculation. Let me do a Roche lobe calculation. Just do it for. I mean, it varies too. It differs. Okay, give you an example. A rocky planet will have a Roche limit, that is to say, a closeness by which it can get to the star before it gets torn apart, that's closer to the star than, say, an icy planet. Icy planet's made of water that's not bonded as tight as minerals and rock is. So the Roche lobe for a watery, icy planet like Pluto would be farther from the star before it starts getting broken up. It would get broken up, while it was still farther away. A rocky planet could get closer. So you have to have two different calculations, one for a rocky planet and one for, like, say, an icy planet. Okay, so it's not a direct answer. I can't just say 300 miles, because it depends on the mass of the star, the mass of the planet, what the planet's made of, etc. Yeah, okay, but it's a very good question.
A few more questions if we could. Yeah. Okay, Daisy and or Zoe wanted to know, did they read correctly that there's a comet that hasn't been visible for thousands of years that will be visible next month? I want to know about this too. That sounds interesting if it's true.
Yeah, Daryl was going to talk about that tonight if he could have joined us. It's Comet 2022 EW, I think, and it's from the Zwicky Transient Facility, which discovered it. It's a comet that's currently in the constellation Bootes, and it's moving its way through the sky. And by February, actually end of this month, it's going to be above Polaris, and we can see that. And we're going to be imaging this comet. It's moving so fast that we'll take a photograph of it, and we come back 5 minutes later and take a photograph of it again. You'll have seen that it visibly moved in the sky. And I like doing that because it shows that the universe is a dynamic place. But yes, it doesn't have an official name like Comet Neowise or Halley's Comet or Hale-Bopp. It doesn't have anything good like that. It's just 2022 AF's Zwicky Transient Facility object.
And speaking of transportation, you're giving me perfect segues. I don't know if I don't know. Anyway, Michael has a question about wormholes. Could a wormhole transport light faster than light? Have we possibly observed this?
We have not. Okay, we don't have any proof that wormholes exist. And a wormhole is also known as an Einstein-Rosen bridge, and that's something I actually was doing a show about this on somebody else's show and talking about this actually. But the Einstein-Rosen bridge concept is really interesting. The problem with that is we would have to use a black hole to help generate the wormhole. And the problem is there that if you enter the event horizon of a black hole, well, space becomes so deeply warped at that point, so deeply warped that you'll never get out. You'll just spin around. That's why light can't get out. Okay, light doesn't have mass, and gravity affects mass only. So how is it that light can be trapped by a black hole if it doesn't have mass? Well, because black holes warp space itself, and light is constrained to follow the fabric of space, like a car on a hill. Okay, the car has to follow the hill. It can't go plowing through the hill. It has to follow the hill. the undulations of the hill, the car follows them too. Well, light is the same way. If space is deeply bent, light follows the curve of space. And if it's very deeply bent, it could turn around on itself. Like once you get past that special place called the event horizon in a black hole, and you'll never get out. So to make a wormhole where you could go into an event horizon and come out somewhere else is next to impossible. That there's no way that we see that you could survive that, because you'd also be subject to something called spaghettification, where you're, a very technical term.
I actually remember that term.
But you do.
That one sticks.
Yep. And,
But is is a wormhole a black hole? Because aren't those two different things?
yes, they are, but they're you would use a black hole to actually build a black wormhole, because the wormhole itself, the black hole would connect to the opposing side where you come out, right? And that's known as a white hole. And that the trouble with these is stability. There's really not going to be a whole lot of stability.
Well, that's it.
Okay, that's all.
That's
you know.
The rest is okay.
Now, I mentioned this story. I talked to Kip Thorne, who he did the technical consultation for the movie Interstellar, and I was sitting with him, and we're talking about black holes, and he was talking about black holes as being time machines, saying you can actually look back in time with a black hole under certain conditions. You'll at least see information coming out of the quote unquote white hole, okay, that you are bringing into the black hole, and you'd see it coming out of the white hole before you enter the black hole. So I think that's pretty cool, right? And it was a good talk, and we talked about that, and it sort of, some of that went over my head because he was talking about certain characteristics that I had yet to be familiar with. But I will say that the concept of a white hole probably doesn't really truly exist. So the next thing is, could you use something outside the event horizon and make that in a kind of like a very quick accelerator for your wormhole procedure? And the answer is, well, maybe, but that's even more unstable than using the other. So wormholes have yet to be proven, shown, observed. We've never seen them. Yeah.
I have a question.
Yes, ma'am.
See, that's the thing. I hear other people's questions, and I hear conversations, and it gets my mind going in a million directions. Okay, the unofficial theme of the show has been light is heat. Okay, so if enough light gets trapped in a black hole and heats up, what could happen? Could we not have an explosion where all of it comes out? Could it not maybe form a stellar nursery, eventual galaxy, life? I mean,
well, isn't a black hole could be a new universe? Who knows?
Well, that's what I mean. Maybe it is an alternate universe, kind of, maybe even an alternate timeline. Because if it can't ever escape, where is it? Does it exist? How can we prove it? I mean,
and all those questions are questions that we can't answer. Nobody can.
Are there any theories of possible anythings in a black hole?
Yeah. I mean, I make a joke. Maybe our entire universe is the interior of a black hole.
It could
Just
be.
a very
That's
large
why we
one.
don't know the end. Maybe the microwave kind of background is
cosmic microwave
the
background
edge of the black hole.
Maybe or not. I don't know.
The opposite of an event horizon.
Well, actually, we can show that the universe is about 92 billion light years in diameter, actually, not 13.8 billion. That's a pretty big. Yeah, but then again, and I'm not saying that I don't believe that this is a black hole, but I'm just saying that it's as good a theory as any, right? Mm-hmm. Black holes. The thing about black holes is, people talk about a singularity. They say it all gets constricted to an infinitely small point in the middle of a black hole. Well, we all know that doesn't happen, okay? It's just that our physics breaks down. And just like when we talk about gravity at the Earth, we say that gravity acts like it's acting at the center of the Earth. But the Earth is massive. It's 8,000 miles in diameter, okay? 25,000 miles around. So it's not a singularity. It's not a single point of gravity, but gravity acts like it's at the center. So when we talk about a black hole, we talk about the singularity that point at the center of the black hole, but the black hole has a size. M87's black hole in that galaxy in Virgo, that black hole's bigger than our solar system. Okay, well, how could it be such a big size? It could be that big a size because it's been ingesting stuff and it's grown. Its Schwarzschild radius, the radius of the black hole beyond which is the event horizon, is getting bigger and bigger and bigger with the more stuff it absorbs. So, but when we talk about it, our physics can only talk about the actions as if we're acting at or having them apply at the center of that black hole. Just like with gravity of the Earth, we talk about the force of gravity, between the Earth and the Moon. It's the equation is, capital G, big M for Earth, little m for the Moon over r squared. What's the r squared? The distance between them. How do we measure the distance? Center to center.
Right.
Okay, so the physics is defined a certain way, and the physics is set up a certain way, but in the same way with black holes. So it sort of breaks down when we talk about black holes a little bit, and that's why they're so mysterious still. So hopefully that kind of sheds some light on that. But what's inside a black hole? Now that's an interesting question.
That we can't answer.
Well, I mean, again, we now know that when it gets inside a black hole and light gets inside a black hole, it's going around forever, right? We also know that black holes give off lots of X-rays. Black holes give off copious radiation. How's that happening? It's happening at the event horizon, at that magical never come back from space, that never, that border to oblivion, okay, the oblivion border, if you will. Okay, that location is a very tumultuous, turbulent region because there's a lot going on there. You've got light going around, light speeds, right, zipping around those holes,
literally,
very fast, yeah. And some of them are going like this and going and going away, hitting and going away. They're blurry like I am right now, So, but they do, they'll whip around, but then sometimes they get really close and come back and finally go right in, zoop, then they're gone. They go inside. What happens when they go inside?
We don't know, right?
No one's ever come back.
Well, if they keep getting bigger and bigger, I had two questions, but I'm going to merge them together in one because we have some from Chad and we're getting low on time. The way you're making it sound like the black hole gets bigger and bigger, it makes me think of like star-going red giant. Like, could it explode at maybe like another big bang? And if we had another big bang in an already present universe, what happens then? Everything gets ripped to shreds? This previous universe gets ripped to shreds and now it's a bit of both? Or
well, as far as we know, the only time black holes ever caused a major disruption is when two black holes were orbiting each other and they collided and crashed into each other. That collision created such a big, powerful explosion from that collision that it created ripples in gravity and space-time, and those were known as gravity waves. Cool. And we saw those. Very impressive stuff, man. Let me tell you. So, but black holes themselves, left alone, a black hole will eventually evaporate. Okay?
Really?
Yeah. There's nothing. Yeah, the reason is because just like big stars, there's loss of energy at the black hole, and the black hole is got a very turbulent event horizon location, like I mentioned. So there's all kinds of stuff going on out there. Lots of radiation being given off. Well, you can't give off radiation without losing something, right? I mean, you're losing energy. I mean, it's not being created inside the black hole. It can't be created nor destroyed. So if it's being given away, then there's less. And do that for many billions of years, and your black hole could eventually evaporate. Now,
and then what's left in its place?
Well, there you go. That's the philosophical question.
Well, but if we saw it happen or know that it happened, what's there now?
I can't answer that because I don't know that we ever have.
It's covered by a dark dust cloud in this universe. We can't see it.
I mean, can stars start to be created there? Can anything? I mean,
well, that's the thing. I mean, stars are created anywhere there's clumping going on in the universe, right? And clumping, like we saw in these dusty clouds, okay, clumping is something that's really important. Like, okay, let's take this object for now. Okay, this beautiful object. Yeah,
Wow.
this is called L1527. This is actually a star before it's a star. Okay, this is a protostar captured by the James Webb Space Telescope. And yeah, and so you're actually looking at this infrared image, and if you look closely, you can see little filaments and structures. Those are caused by eruptions on the protostar that are blasting material out. Protostars are very violent. They're not just these quiescent little percolators, okay? They can be very violent. And we're seeing this protostar, and eventually it'll become a star. And this might become a nebula like our Iris Nebula, for all we know, okay? Or like our Lagoon Nebula. This could end up causing a bunch of other stars to form. Now, that triangular thing on the left and on the right of dark, that's actually dark dust. Okay, and the way the protostar is giving off its energy is in these cones up and down like that, and so that's why you see it like this.
So is it in front of the dust then?
I think this is behind that dust, and it's actually or embedded in the dust. Okay, and the energy is coming out in these shapes right here.
So what is this? Something before it's a star. What is this?
It's a protostar. It's a star.
Protostar.
It's what our sun looked like before it became the sun.
Before it turned on?
Before it winked on, that's correct.
So, but
go ahead, Amanda.
Stuff is leaving this protostar. What is it? Just gases forming and doing their things, or
it's dust, it's gas, okay? It's hydrogen gas and other elements that are being made in the star. That
is this in a stellar nursery? Is this a close up of something in a stellar nursery?
I'm not sure if there's more to this, but this is a protostar that's embedded in the cloud that made it, okay. And what happened is these ejected material from the star above and below have carved out cavities in this dark area, in the dark nebula, and you can see that the cavities are a very specific shape. And that could be characteristic of the geometry of how the star is being made inside of here. Maybe it's a rapid rotator. I'm not sure. I mean, maybe it's actually rotating this way. If you look at my finger, you can see maybe it's rotating this way and blasting stuff like this way and that way. So it's kind of going like this.
Mark, I have a question. It looks like it's already glowing right now. Is it just because it's the infrared? And if we were to look at this, we wouldn't see the glowing light of the star because it hasn't winked on? You
wouldn't see it like this, correct. Okay. It would be in the visible light. There might not be any inkling. There might be. I have to look and see if this actually has. But this is a dark nebula, and the protostar is lighting up the dark nebula.
That's cool.
Isn't that cool?
Mm-hmm.
Yeah.
And I feel bad. I know we had more questions from chat. I'm sure Tara had a million questions. I'm sure Mark actually had a program he wanted to do, and I kind of I don't know. Just some of these topics, I have a gazillion more questions, and we're just about out of time.
Well, it saves us more for next week. That's all.
Yeah.
So not a big deal.
Just everything about tonight was fascinating. What a way to kick off the new year, eh?
Yeah, I really enjoyed it. And this is again, if you have more material than you need, it's always better, right, guys?
Oh, of course.
So we do. And if you get a chance, guys, when you get a chance, check out our skytourlive.com. Okay. Again, skytourlive.com at the bottom there, or skytourlive.org. We thank you, PG. We are an organization dedicated to teaching people all about the night sky, and we want to make sure that everybody enjoys it, learns from it, and then gets something for it. So you go there, and we have a database, and we actually have our data online. As soon as an image is taken, it goes up to the cloud and is available to you literally in 30 seconds or less. And you can see the image we just took and take it down onto your desktop and enjoy it all you want, because that's what we do. And if you want higher res versions, well, you could become a Patreon subscriber, and then you get the very, very high res images that you can turn into a gigantic, 30 by 40 poster in your wall or something. So it's all for you. Just it's all at your beck and call. But join us at skytourlive.com. It'll take you to skytourlivestream.org or Skytour Livestream, our channel
on YouTube,
right? Or it'll take
Facebook.
you, or take you to Skytour, the Skytour Patreon, where you can join us there too.
I gotta take us to our next show, so I apologize, but hopefully we'll see you here. Same bat time, same bat channel.
You got it, Robin.
Sweet. Stay safe, everyone.
Good night, everybody.
All.
Thank you.
Bye.
Thank you for coming.